Now, dear student, it is my second lecture class, and now I will be discussing firstly the harmonic motion representation by a complex method. This you already studied earlier in +1, +2 classes. So you can represent a vector v in xy plane where the real number of the complex number will be expressed on x-axis and imaginary part will be represented on the y-axis. And you know that j is nothing but it is the square root of -1. So here this is the vector v is equal to a plus j beta, where theta is known as argument and this is basically a and this is equal to b here. So this will become simply tan inverse b upon a. Similarly, your this vector OV is also known as it can represent by r here, and this r can be given is basically nothing but it is the modulus of complex number, complex vector, and it nothing but it is equal to a square plus b square root. So here you get the two component here. This is also known as a rectangular form of SHM representation. So you can write the same vector which is given by a plus j beta in the form of this a will become in the argument and the mod form nothing but r cos theta. And this b will become r sine theta. So you can represent the same vector as r cos theta plus j theta. And now you can write this in exponential form, nothing but e j theta. It is known as the exponential form or Euler's formula. So now for a rotating vector having a amplitude of r, having a circular frequency of omega, this theta is nothing but omega t. So I can write this theta is equal to omega t here, and you are getting our required SHM notations in terms of exponential form. You can make a differentiation of this equation with respect to t, and you will be getting this equation here. When you multiply this equation by j once more, you can take j out here and it become like this. Now if you compare our earlier equation of velocity vector, which was basically nothing but x sine omega t plus pi by 2, and you have seen that our x omega. You have seen that this vector velocity vector is leading the displacement vector by 90 degree. So I can say here that when you multiply this complex number by j, it is equivalent to rotation of the vector by pi by 2 in the direction of frequency. Similarly, if I multiply this, if I make a one more derivative of this with respect to t, you are getting this equation, and you can take this j out here. It becomes simply minus 1. It means if you multiply the vector by minus 1, then it is equivalent to rotation of the same vector by 180 degree. It's nothing but it is basically the acceleration, and it is basically given by x omega square sine omega t plus pi. So this is the basically a complex method representation for a vector. Now let us come to the very simple article, that is your addition of two simple harmonic motions of the same frequency. You are having a same frequency here. So suppose you are having a particle which is simultaneously subjected by two simple harmonic motions having the same frequency in the same direction, then you can add these two frequency SHM motions, and the resultant will also be a simple harmonic motion. Suppose you have, so for that you are having a two methods. The first one is your analytical method, and second one is your graphical method. So you are having these two simple harmonic motions having a phase difference of alpha. Here this will be basically in terms of radian. You have to note this point here. So when you make a summation of these two simple harmonic motions, then you can write these two here, and the resultant is suppose given by this, where beta is the phase difference between the x1 with respect to x1. So when you open these two equations, these two one, and when you compare the two cos omega t and sin omega t terms on the both side, then you will be getting a two equations. The first one is your x cos omega cos beta is equal to x1 plus x2. It will be opened into cos alpha here. Similarly, when you are having a sin beta term here, it will become like this. So here you can find the resultant amplitude of the resultant vector, nothing but the square root of the sum, and you can find the phase difference with respect to x1 for the resultant vector is given by uh, like this, nothing but you can make this equation here. There is not x sin beta upon x cos beta, and once you got this beta and x here, you can represent the resultant vector by this. Here again your beta should be in terms of radian, and here you will be getting a beta in terms of degree usually. Then you convert this into radian here. The second method is your graphical method. So here uh, you will be first plotting the x1, nothing but sorry, this is your your x1 is equal to x1 sine omega t. You plot this vector first, then you plot the second vector x2 here, nothing but x2 sine omega t plus beta. Then you can make a parallelogram here. This is parallel to this and this is parallel to this, and you can make a resultant SHM vector given by this is given by nothing but x sine omega t plus beta. Sorry, this is your beta here. Okay, this should be alpha here. So here when you use the graphical method, your both the equation must be in sine form, and this angle you should find out in the degree here. Then you can plot these two equations, and in that way you are having a summation of two simple harmonic motions. You can have this example here. It is very in analytical form. You can have cos and sine, and you can analytically solve this problem. But if you want to solve the same problem by a graphical method, then these two should be in the sine form. So you convert the cosine into sine, and you again convert this value which is in radian into degree, and then plot these two vectors on a graph, and you can have a resultant vector of these two SHM. Now let us come to the next article. This has been solved here. You can go through this. Now one more. Now let us have example here. You are having a these two simple harmonic motions. One is x1 is half cos pi by 2, and second is x2 sine pi by 2, and second case is x1 2 cos pi and x2 is 2 cos 2t. Is the sum of these two vector is periodic motion? You have to tell this, and if it is so, then what is its period? So for the first equation, for the first case, this is your basically a omega. So this is your omega here, nothing but pi by 2. So you can write the period of this nothing but you can say 2 pi into f. F is the frequency in hertz. It become 2 pi upon time period. So you are getting a time period nothing but 2 pi upon pi by 2, nothing but 4 seconds. Similarly, you can write 2 pi upon this omega. It become a period of second wave. Now so your first wave will be having a time period of 4 seconds. Second will have a time period of 2 seconds. So if these two time periods are integral numbers, then your resultant motion will be simple harmonic motion, and for that your LCM of these two time period will be the time period of the resultant motion. So here LCM of these two nothing but 4 seconds. So this is the time period of the resultant SHM. In the second case, here you are having a time period nothing but 2 pi upon pi is equal to 2, and in this case time period is equal to 2 pi upon 2 is equal to pi. So it means these two are not the integral multiple of the time period. So the resultant SHM will not be a simple harmonic motion. So you are having a time period of the first wave is 2 seconds and second for pi, and these two will not have a common multiple here, so it will not be a periodic motion. Okay, all right. Now let us come to the next point, that is your beat phenomena. Suppose you are having a particle subjected to a two different harmonic motions. Here the frequency is different. Okay, and this frequency will be slightly different here. I will be telling why it is so. The resultant of these two motions can be given by this. So, so for this, so if omega 1 and omega 2 are different, then resultant motion is not sinus SHM. But you will be getting an interesting feature here. And the feature is that when omega 1 and omega 2 are approximately equal, or omega 2 is equal to slightly more than omega 1, in that case the phase difference between the rotating vectors will keep on shifting slowly and continuously. So you will be getting a two specific time where this value, this vector will be either in phase with respect to these two, or they may be in phase. So you are having a two conditions here. When the phase difference between these two is either in phase means 0 degree, and out of phase means 180 degree. So in this case, at a 0 degree they are in phase, so resultant amplitude will be A plus B, and when they are out of phase, resultant amplitude will be A minus B. So it means when the frequency of the two simple harmonic motions are approximately equal, then you are getting a continuous variation of amplitude and their phase difference. So the resultant amplitude will continuously vary from A minus B to A plus B. And because of this reason, and the frequency of this uh, this one will be equal to omega 2 minus omega 1, nothing but delta omega. So this is the frequency of this one. So this whole phenomena is known as a beat phenomena, and frequency of the beat is given by omega 2 minus omega 1. And it is necessary that, so if you want to experience this beat phenomena distinctly and clearly, then your A and B must be equal. In that case, you will be having the amplitude 0 to 2A, and you will be getting a clear and distinct beat. So this beat phenomena is graphically shown here, and this is your basically a time period of the beat phenomena is nothing but 2 pi upon frequency of the beat, nothing but omega 2 minus omega 1. So you can see the beat phenomena is working here, and you can make a enveloping curve for this, and this is your out of phase having a plus B, and this is the this is basically in phase, and this is your basically a out of phase, and having a minus B. So this can be explained mathematically here now. So you are having a omega 2 minus omega 1 is given by this. It means they are slightly different. So when I write the value of x, resultant vector is nothing but this value. So you can open this one. It become b sine omega 1 t cos delta omega t and cos omega 1 t and sine delta omega t. So you can combine the like terms, sine omega t term here. You can combine cos omega t here. This is the resultant vector here, and you can see here these amplitude of these two terms. This is the amplitude of the first one, amplitude of the second one term here, and these two terms are time dependent. So it means they will vary continuously with respect to time, and these two terms, this is having a sine omega t, this is having a cos omega 1 t here, so they are having a basically 90-degree out of phase terms. So the resultant amplitude of the motion can be given by the square root of this plus square of this, having a square root of whole thing. So when you solve this equation, this is your a square plus 2ab cos delta omega t, and then you are having a b square here. So you can say here that x is a basically function of cos delta omega t, and this can have a value of maximum value plus 1, minimum value minus 1. So it can have a plus b to a minus 1. So this is how you are getting the beat phenomena here for a two different frequency SHM motions, provided they are very close to each other. Now let us solve this example here. If you are having a two simple simultaneous motions here, x1 is equal to a sine omega t, x2 is equal to a sine omega 2t, and omega 1 is slightly higher than omega 1. It means omega 1 is equal to omega 2 plus delta omega. So you need to show that for the resultant beat phenomena curve, the slope at this time is given by this, and this will become 0 when this condition is satisfied. So here you can find the resultant of these two SHM vector, that is in x1 plus x2 here. Then you can apply the well-known formula of sine A plus sine B, and you can write this term here. Nothing but sine omega 1 plus omega 2 by 2 into cos omega 1 minus omega 2 t. Then we will be finding the differentiation of this equation here with respect to t, and you can use the differentiation by differentiation here, and you will be getting these two terms. This is your 2 sine omega t here. Then you can write the differentiation of this term here. It becomes minus omega 1 minus omega 2 by 2 into sine omega 1 minus omega t here. Then you can make it differentiation of first term and then multiplication of second term. Now for a given time period, that is your given time period here, when you put the value of this time period here, then you will see that this term so when for this time period here, so you are getting this equation here. So you can simplify this and one term will become 0 here. So to make this slope, this is basically slope equation. To make it this slope 0, it will become sine and pi. It means When this complete term is equal to n pi, then your slope will become 0 here. And when you open, then you do this, it becomes simply omega 1 plus omega 2 upon omega 1 minus omega 2 into pi by 2 is equal to n pi, and you can find the desired expression which you need here. This is nothing but you are getting this equation here. So you can do the problem like this. Now let us come to the important article here. Now this is very important article here, and so you are having a harmonic force. You need to find the work done by a harmonic force on a harmonic motion. Suppose your harmonic force is given by P naught sine omega t, and this force acts on a body, and under this harmonic force the system will vibrate with same frequency but with some phase lag. Let the motion of the harmonic motion, because of this harmonic force is given by x naught sine omega t minus phi. It means the motion generated by this force is having a phi phase difference lag. It is lagging by phi. So one can find the work done. So one can find the work done by the force P during a interval when the body moves by a small displacement dx given by this. This is the elemental work done for a elemental displacement of dx. I can write dx in this form. So you can put the value of this P, you can put the value of this displacement here, and you can find the elemental work done for dx displacement. And if you want to find the work done per cycle, for which your omega t will vary from 0 to 2 pi, or you can say t will vary from 0 to 2 upon pi. So your work done will be nothing but it is the integration of this whole term. So here you can put the value of p, nothing but p naught sine omega t. You can put the value of dx, make a differentiation of this with respect to t. It become omega x naught cos omega t minus phi. Now you can integrate this equation as usually. You can take these common terms out. You can expand these term here, and it will come out to be sine omega t cos phi plus sine omega t sine phi. Then you can have an integration over a one cycle period 0 to 2 pi upon omega. Now it is nothing but sine 2 omega t by 2, and this is nothing but it is equal to 1 minus cos 2 omega t by 2, and you can integrate this equation, and after that you can put the limits to this here, and you will be getting this final equation. It is your p naught omega x naught. Your omega will cancel here. It become pi p naught x naught sine phi. Now I will conclude this equation in a very interesting manner. If phi is equal to 0, it means when the force is in phase with the displacement, then no work is done per cycle. On the other hand, if phi is equal to 90 degree, if you say this is your P naught here by omega t, and when phi is equal to 90 degree, it means it is lacking. This is your displacement x having a 90 degree here. So when, on the other hand, when phi is 90 degree, it means when the force vector is leading the displacement by 90 degree, and you also know that your velocity vector is also leading the displacement by lead the displacement phi x by 90 degree. It means you are having a velocity is also in this direction, is in the phase with the displacement. Then in that case, you are having a work done by the cycle in a cycle is given by this equation. That is your, it become 1 here. So now if I correlate this derivation for a undamped force vibration, in for that conditions you are having a phase difference graph. So here you are having a ratio of omega upon omega n, and here you are having a phase difference phi. So in this one, this is your one value. This is the resonance conditions for the undamped force vibration, and here the graph will be like this. This is your zero phase difference, and this is your 180 degree phase difference, and this is your 90 degree phase difference. This graph shows that before the resonance, the force and the displacements are having a 0 degree phase difference. At the resonance, it transforms from 0 to 180 degree instantly, and in between you are having a 190 degree here, and beyond the resonance you are having a 180 degree phase difference. So you can see here in the undamped force vibration, when damping is 0, then no work will be done by the external force except at resonance. So you can see here, so except this point, for all other points, at all other frequency, there is no work done by the undamped force vibration except the resonance. And for this, and for a damped system, you know that for a damped system, there will always be energy required to keep the system vibrating at any frequency. So you can see this formula is useful to find the work done by a harmonic force on acting on a body, which basically generates a harmonic motion. Now let us solve a problem based on this. You are having a force P naught sine omega t, and this acts on a body which get it, that is its displacement is given by x naught sine omega t minus pi. We have been given a value of P naught is equal to 25 Newton, x naught is given by 0.05 meter, and omega is given by 20 radian per second. You need to find the what is the work done during the first second, and then the first 140th second. So in this, uh, if you were this time period, this time is an integral multiple of time period. Then you can use this formula straight away. You can use this formula straight away here. If your given time period is an integral multiple of this. So here you can see here your time period nothing but 2 pi upon omega, nothing but 2 pi upon 20 pi, it become 0.1 second. So basically it is nothing but it is basically equal to 10 cycles. So you can use straight away this formula here to find this. But if the time period for which you want to find the work done here, it is not integral multiple of this, then you have to go to the basic formula of this. Then you apply the basic mathematical concepts and you will find out the general equation of work done for a arbitrary time period t1, where t1 is not a integral multiple of tp. And here again you can see you are having the same equation, you are having a same value here. It is simply your earlier you are having a phi here, that phi has been simply changed to minus phi has been changed to this here. This is your phi. So again you can write the form, you can use the formula here, sine A so you can have a formula here, sine A cos B is equal to half sine A plus sine A minus B. So you can use this formula here and can have this value here. So again you can solve this equation and you are getting P is given by, this is your work done for a some time value of t1 here. You can put the value of all these parameters and then you can also put the value of t1 and 0 here, you put the limit here, then you will be getting so this whole thing will come out to be 39.25 and this will come out to be 6.9 into 10 raised to power minus 3. Now once you got this equation, you can also use this equation to find the first case value and you will be getting the work done for a first second when you put the t1 is equal to 1 second here. This comes out to be this value. And you can also use this formula to find the work done for any time period, any time, that is your 1 by 40 second, and again you put the value of T1 here, that is your 1 by 40. This is again T here. So you get the value of the work done by this 1 by 40 second. That is the first 1 by 40 second of the force. And the last article of this chapter is Fourier series and harmonic analysis. So generally you will see that forces which are arising out of machines are usually periodic, but more often they are not harmonic motions in nature. So that's why we need a Fourier series and harmonic analysis for this type of motions. So as you know that periodic motion is one which repeat itself after certain time interval, and this will be having a time period of t tau. So you can find so for a mathematical theory, this periodic motion can be represented by ft as a function of t, and having a frequency. If you know the time period, you can find the frequency here, then nothing but 2 pi upon omega, nothing but 1 upon f. It become this is your basically a, or I can write from this omega is equal to 2 pi upon tp time period. So if you know the period of motion, you can find the frequency, and if the periodic motion can be represented by this curve ft as a function of t, then I can represent this function t as a sum of sine and cosine terms. So they are basically having a uh, n number of cosine terms, having a n omega t frequencies starting from omega t, and then you are having a sine infinite number of sine terms having a frequency from omega to infinity n omega. So I can represent this complete series in this summation form, where n vary from 1 to infinity. So here all a coefficients are representing the amplitude of cosine series, and b representing the amplitude of sine series, and these and a naught is basically some constant term, and so these constant terms a naught, a and b's can be found out numerically or analytically, provided you know the ft as a function of time. So this equation 1.81 is known as a Fourier series. So in this Fourier series, you are having a frequency omega t, 2 omega t, and so on. So the omega t is known as a fundamental or first harmonic of the ft, and n omega is known as a nth harmonic of the same function ft. So the branch of mathematics which split the periodic motion into a harmonic functions is known as a harmonic analysis. So I will be discussing how you can find analytically the various coefficients of this Fourier series, so that you should able to calculate the forces etc. for a real machines vibrations. So here I will like to tell one more thing. Your A0 is basically representing the average height of ft, a function ft, and this will be equal to 0 when ft function is symmetric about x-axis or time period, time axis. This you will be able to understand when I do the analytical math one to solve this. Now to solve this harmonic, to solve this Fourier series or to do the harmonic analysis, you are having these 5 formulas which will be very handy to calculate all the coefficients here. So for a given time period t to t omega t, it is simply basically a one cycle. Then you are having a cos term, cos n omega t and cos m omega t. So if you are having an integration of this type, this will be having a 0 value when m and n are not equal, and it will be equal to pi by omega when m and n are equal. The same thing, same condition will apply when you are having a sine and sine term. Again, you are having a 0 for all unequal value of m and n, and then equal to pi by omega when they are equal, m and are equal here. Then the next formula is, it is basically cos and sine. Then you are having a sine and cos here. Again you are having a n omega t and m omega t. Again for a one cycle it will be equal to 0 for all values of m and n. Then you are having a this formula again for one time cycle, and it is again equal to 0 when it is a cos only and it is a sine only. And for these two formula you are having a 0 value for all values of n. So these 5 formulas are very handy to find the coefficients of that Fourier series. And here m and n are basically non-zero integer. Now to find the first value, to find the a naught value here, then you will be using these equations here. Okay. So in this case your ft is nothing but, let me write ft again here, it is equal to a naught plus summation of n is equal to 1 to infinity a n cos n omega t plus b n sin n omega t. So if I integrate, this is nothing but ft. If I integrate this equation for a one time period, then you, as per these two equations, your all cos and sine term will be 0 except this first term. All right, and basically you are having a naught into dt 0 to 2 pi by omega, and it comes out to be like this. So from that you can find the this term here. This is given by omega upon 2 pi into integration of the ft function over a one time period. Now similarly, if you want to find an, if you want to find am here, then we need to multiply it by cos and omega t. Again you multiply this by cos n omega t, then you are having a cos n omega t cas n omega t here. You multiply this by cas omega t here, then you will be getting only the one term out of all the numbers which is non-zero, and all other numbers uh, that number which is not zero here is given by cos square n omega t when n is equal to m, and this is basically having a uh, cos n omega t sin n omega t. It is 0 for every value of n. You are having a cos square n omega t, it is equal to 1, and for all others a naught cos n omega t, again you are having a 0 value. So for this case you are having a this equation, it is basically equal to 1. Hello, it is equal to 1 here, it simply become this value. So you can again find the value of a n from this, it is given by this. So similarly, if you want to find the b value of the Fourier series, then multiply it by sin n omega t, and again, okay, this is missing a, okay, now this basically, now when you are having this value here, so again you will be having 0 to 2 pi by omega, or I can write t plus 2 pi ft into sin n omega t into dt, and again here you will be getting only one term, that is nothing but equal to omega upon pi t into t plus 2 pi upon omega sin square n omega t into dt, and this becomes simply into bn, it becomes simply bn into pi upon omega, and you are getting a value like this. So you can find the value of a0, you can find the value of an, you can find the value of bn, and then you can put the value of n in these two conditions, in these two equations, 1 to infinity, 1 2 and so on. So in that way you can convert a periodic motion into a simple harmonic motions of n frequencies here. Now let us solve a problem based on this. This is a problem which I will be solving for this one. So here you are getting a time period. This is a tooth profile having a time period is equal to 0.1 second, and you can represent the Fourier series ft is equal to a naught plus summation of n is equal to 1 to infinity a n cos n omega t plus b n sin n omega t, and you need to find the value of a naught, a n, b n, and you need to derive the equation ft here for this periodic motion. So here you can see for 0 to, for t is equal to 0 to 0.05, your xt x is equal to this, xt is equal to 200 t. You can have a equation of line here. You can have a coordinate for this point in terms of xy, and then you can write this equation. You are having a 0 0 here, and for t is equal to 0.05 to 0.1, your xt is equal to minus 200, sorry, minus 200 t plus 20. Okay, so you are having these two equations here. And what is your omega? You already find Tp here. Your omega is nothing but 2 pi upon Tp. It comes out to be 20 pi radian per second. So you know everything here now. So to find the A naught, you are having this formula, that is nothing but Ft dt 0 to omega t omega upon 2 pi, and then this is your omega upon 2 pi. So you can find the value of this nothing but 10 here, and you can write the equation this again, this Ft having two components, 0 to 0.05 and 0.05 to 1. You integrate this separately, and you will be getting a naught is equal to 5. And if you see here, this is the average height of the periodic function, and this again you will find this is the average height. This is your 5. You can again find this area of the triangle divided by time period. It will come out to be 5 here. It is the average height of the periodic motion. Similarly, if you want to find an, again for an, you are having omega upon pi 0 to Tp into Ft into cos n omega t into dt. So again you are having two components for Ft, 0 to 0.5 and 0.5 to 1, and then you can having this formula here, 200t, this one here. So you can solve this equation by integration by parts, and I can read the formula here, that is your integration of uv dt is equal to u integration of v plus minus differentiation of u and integration of v and then whole differentiation. So you can use this formula here to find the value of this integration, and you will be getting a an is equal to this value. So here for this value you are having a two possible solution when n is equal to odd and when n is equal to even. When n is equal to odd, it means when cos n pi is equal to cos 180 like this and so on, it become minus 1. So you are having this equation. When cos n is equal to even, then you are having a cos 0, then you are having a cos 360 and so on, it become 1. So you are having a 0 value here. So only for the odd number an will be there, and while for even number of n, an will be vanishing. Similarly, if you want to find the bn for this, it is equal to bn, you are having a omega upon pi 0 to omega upon 2 pi ft into sine n omega t into dt. So again you are having this integration here. When you put the value of ft for the two subcomponent of tp. So here again you can have an integration by parts, and in both the cases you will be getting a zero value here. So it means bn will not be there. So only term which you are having in this periodic motion will be having only a naught, and you are having a an for only odd numbers. All right. So you can write simply here a naught plus summation of n is equal to 1, 3, 5 to infinity. Then you are having a an cos n omega t, and you can put the value of an is already given here. This an is given minus 40 upon pi square n square. So you can put the value of n, 1, 3 and 5, and you will be getting these equations. This is how you are converting a periodic motion into a series of harmonic functions. And once you got this series, you can apply this to our standard vibration analysis and can find the number of forces because of every terms. So this is all about this lecture class.